But if you were to add some oil or liquid to this pan, the transfer of heat would be much faster. This should explain how the flux helps to spread or transfer the heat from the tip of the iron into all of the metals that it touches. The hand soldering operation usually happens very quickly, and it's impossible to see everything that's going on, since the parts are very small. So let's examine an animated hand soldering operation to observe how everything works. First, the tip of the iron is applied to the junction of the land and the lead to be soldered. This starts the heat flowing. Next, a heat bridge is formed by touching the solder wire to the same junction. This starts the flow of the flux and the initial melting of the solder. The flux moves away from the heat and ahead of the solder over all of the metal surfaces. The heated flux removes oxidation or contamination from the metal surfaces. Everywhere the flux touches, it helps to heat up the metals. All of the metal surfaces need to be at the proper temperature or the solder won't bond properly. Now the solder wire is moved over to the opposite side of the land while the solder and flux continue to melt. Liquid solder will move toward the heat. That's why we want the solder to flow from the opposite side of the heat source. Otherwise, we might not get enough solder to flow over onto the unheated side. The flux is pushed along by the solder as it performs its cleaning job. As it moves in front of the solder, it also floats away the loose contaminants. The flux and oxides will end up pooled around the edges of the land after the soldering operation is completed. Now the solder is chemically bonded or wedded to the land and the lead, just below the surface of the metals. Portions of the lead-free alloy mix with copper from the circuit board, forming a new type of metal in the area where they bond, which is called intermetallic layer. Wetting is a term we use to describe the adhesion of the solder to the base metals. Properly wetted solder typically feathers out to a smooth edge. Non-wetting is where the solder clumps like a ball on top of the metal. One way to think of wetting is to observe a sheet of copper with water flowing over the surface. If the copper is oxidized or contaminated, the water will bead up on the surface into little balls. After we clean the copper and remove the oxidation, notice the difference? In this case, we could say that the water wets the surface of the copper, rather than beading up into drops. We'll be talking a lot more about wetting later in this video. But for now, let's get back to the flux and learn more about the different types of fluxes that you may be using in various situations. The different types of fluxes used in soldering electrical connections are described in the IPC J Standard 004. The J Standard 004 separates all fluxes into one of three classes. These classes are based on the activity level of the flux, which essentially defines how strong of a cleaner they are and how corrosive they are to metal. Type L stands for low. Type M indicates medium strength, and H is for, well, you guessed it. Type H fluxes may occasionally be used. Type H flux cleans very well, but has an extremely active or corrosive residue that must be completely removed from the board. Type H fluxes are used in situations where it is difficult to remove oxidation from the base metals. Type M fluxes are less chemically active than Type H and are also less corrosive. Type M fluxes must be thoroughly cleaned off the board to prevent metal corrosion and electrical failure. Generally speaking, Type L fluxes are relatively weak cleaning agents and are practically non-corrosive if they're left on the board. In most cases, your company will select the type of flux you'll be using in order to be compatible with their cleaning systems. But it's important for you to understand that there is a reason to use only designated flux types and to follow your company's standard operating procedures for flux usage and cleaning procedures. The next consideration is the amount or percentage of flux contained inside the solder wire. The J Standard 006 has a table that lists the percentage of flux that different thicknesses or diameters of solder wire may contain. Lead-free solder wire usually has a higher percentage of flux for a given diameter than tin lead solder wire. Generally speaking, once again, the higher the percentage of flux that a solder wire contains, the greater the cleaning action, but there will also be more residue to clean off the board. As you can see, there are quite a few options in flux selection. Your company will decide the specific type of flux and the flux core percentage to use for each application. Flux residue can also be sticky. If these residues are not cleaned off the board right after the soldering operation, they can allow dust and other contaminants to stick to them. Some contaminants can be electrically conductive. If they are, this can create electrical leakage or even a short circuit. Flux cleaning techniques will be explained in Section 4 of this program. Now let's discuss the size of the solder wire. Solder wire comes in different diameters, which is usually stamped on the end of the roll. Selection of the right diameter is an important part of the hand soldering process. For example, if you were to use a very thin solder wire for a large connection, it would take a long time to melt the right amount of solder. Keep in mind that after 3 seconds you run the risk of damaging the component or the circuit board. And if you were to use excessively large solder wire for a very small connection, you might not be able to control the amount of solder that ends up in the joint. Selecting the correct diameter is something you'll learn from experience. Our recommendation is to pick a diameter that is slightly less than half the size of the land that you'll be soldering. Now that you're familiar with soldering tools, solder types, and fluxes, let's discuss the nuts and bolts of how to hand solder through-hole components onto printed circuit boards. Most production soldering is done with automated machines that can make hundreds of solder connections all at once. But there are some heat-sensitive components that can't handle the higher temperatures during wave soldering. Defective components may also need to be removed from the board after wave soldering, and a new component hand soldered back in its place. Regardless of the reason for soldering by hand, we need to be able to make a strong physical and electrical solder connection that will last. The hand soldering process should always begin by preparing or tinning the tip of the soldering iron. We explained earlier how oxidation forms on the surfaces of the metals to be soldered. This oxidation will also form on the tip of your soldering iron. Oxidation acts as a barrier or an insulator, which means that it can slow down the transfer of heat. An oxidized tip will prevent the rapid transfer of heat into the metals to be soldered. Lead-free solder is even more sensitive to a dirty tip than tin lead solder. Notice the time difference between a properly tinned tip and an oxidized tip melting a similar solder connection. To begin the tinning process, we'll take the hot soldering iron and wipe the tip 2 or 3 times across a damp sponge. This will remove impurities and oxidation, but it shouldn't cool the tip too much. If the tip is wiped excessively, if it's gouged around in the sponge, or if the sponge is too wet, the tip could become too cold to use for soldering or tinning. Now let's apply some flux cored solder onto the tip. The flux inside the solder will flow first and chemically reduce the oxides from the tip. Then the solder will flow over the tip and form a shiny coating. This tip is now properly tinned. Tinning is especially important on brand new soldering iron tips. Every time you install a new tip, it's important to tin it right away, or it may become untinnable and unusable. Tinning should be repeated as often as necessary. Whenever you can see that the tip is no longer clean and shiny, you've waited too long to retin. Heat can cause soldering iron tips to become so oxidized that they become unusable. It's a good practice to melt some solder onto the tip whenever you plan to let the iron set for any length of time. This solder coating will keep oxygen from reaching the metal tip to protect it from severe oxidation. It's also a good practice to turn the iron off when it won't be used for an extended period. On some irons, oxidation can also form on the barrel, which is the area between the tip and the handle. If it's not removed, the oxidation on the barrel can also slow the transfer of heat to the tip and keep it from quickly reaching the soldering temperature. Oxidation can be removed from the barrel with fine abrasive or a wire brush. Brushing should be done away from the workstation surface to avoid contaminating your work area. After we've prepared the tip of the soldering iron, we should be ready to start the soldering operation. We'll be using a temperature-controlled soldering iron with a chisel tip. The temperature of the tip will be set at 315 degrees C. Our solder will be 96.5% tin, 3% silver, and 0.5% copper, with a 0.79 millimeter diameter. The flux in the core of the solder will be type M, or medium activity. To demonstrate the basic technique, we'll be soldering a round component lead into a plated through hole. Normally, this type of soldering operation would only take a few seconds to complete, but we'll be stopping the process in order to explain everything that happens as we go along. We begin by gently placing the cleaned and tinned soldering iron tip against the lead and the land. This will transfer heat into both of these parts. Now the solder wire should quickly touch the tip of the iron to melt just enough solder and flux to form a heat bridge between the metals. Then we'll move the solder wire over to the opposite side of the joint, still touching both the lead and the land. When there's enough solder melted into the connection, the solder